Hello, my name is Matthias and I work with the quantum team at Microsoft. Today I'm going to show you work that shows how you can build your own simulator using the Microsoft Quantum Development Kit. This has been worked together in collaboration with my colleagues Maria, Vadim and Sasha. This talk is based on a series of blog posts in the Q# blog in which we have shown how to build your own simulator that you can use with Q# programs. In these blog posts, we have used as examples reversible simulators and circuit diagram generation using QPIC, which will also be serving as examples today in this talk. I'd like to mention that the details of the API, as I'm going to present it today, are going to change in order to make it more general and more robust to use. However, the discussed principles will still apply and will be the same. In order to keep you updated, I would like to refer to the blog posts and the samples that are more detailed, and they will be updated with respect to changes to the API. Simulators lie at the very core of executing Q# programs. This shows you an example Q# program in which we use a lot of high-level and library functionality to describe the Deutsch-Jozsa algorithm. It takes as input a Boolean function described as a truth table and the number of variables of that function. Then control lines and target lines are allocated and we apply the gates that are required to implement Deutsch-Jozsa algorithm, which is like negating the target line, then applying Hadamard gates to all the qubits, and then applying the oracle that implements the truth table or the Boolean function onto the target. Afterwards, unapplying the gates that we have done before using this within apply construct. Eventually, we return true if all the measured control lines evaluate to 0, which would mean that the function is constant and otherwise balanced. In this example, operations like apply to each or is result 0 are just implemented in Q# and refer to other operations. But the very basic operations, which are called intrinsic operations, like x and h, do not have an implementation. These implementations are provided using simulators. We can run this program using a simulator, and one way to do it is, for example, using a test project. In this test project over here, the Deutsch-Jozsa algorithm is instantiated twice in 2 different tests. However, for each of these tests, a different simulator is being used. For the first test, we're going to use the quantum simulator, which is a full state simulator, to run this and simulate the Deutsch-Jozsa algorithm on the whole quantum state for this 4-input Boolean function, and then print whether this function is constant or not. In the second algorithm, we apply resources estimation. So instead of calculating the overall state vector of these qubits, we merely have counters that we update for the gates that we encounter. For example, we want to count how many X gates are in our circuit, or how many Hadamard gates, or what is the cost of implementing this truth table oracle. This is the implementation for the simple reversible simulator of the first blog post in the blog post series. The simulator itself is described by the C# class Reversible Simulator, which is a simple class just deriving from this quantum processor dispatcher, and all it does, it initializes a processor instance in the constructor. So most of the action goes on in the processor class instead. Let's have a look into this class, which is defined in the same file. In this class, we're going to keep track of simulation values for each qubit. This is a reversible simulator and only can act on classical simulatable operations in the Q# program. For example, X gates or multiple controlled X gates, such as the Toffoli gate. We can keep track of the simulation state by assigning a Boolean value to each qubit, which is being done by this dictionary over here. First methods that we override are called whenever we allocate or release qubits with a using statement in Q#. So for every allocated qubit, we just insert a new simulation value into the dictionary that is initialized to false. And when we release qubits, we remove these elements from the dictionary again. Now what happens if we apply an intrinsic operation? Then we call a corresponding method callback in this processor class. For example, when we call x on some qubit, then we can perform this action in the simulator, which inverts the simulation value at that qubit. A bit more complicated example is a controlled x operation, in which we apply an x but controlled conditionally on a set of other qubits, control qubits. Here we invert the simulation value of the target qubit, only if the simulation value of all control qubits is true, which is outsourced to this helper function AND. Other intrinsic operations are reset, which sets a qubit's simulation value to false, or measuring M, which looks up the current simulation value of a qubit, which is either true and false, and maps it to a Q-sharp result value, which is then 1 or 0 respectively. Let us now enhance this very simple reversible simulator a bit further. One thing we would like to do is we want to simulate operations like the one you see here that implements a majority operation. Note that this implementation uses CNOT gates, but also the AND operation in order to save the number of T gates that we require. This AND operation makes use of the fact that it acts with a target gate that is known to be in state 0. And since it's in state 0, there's an implementation with only 4 T gates instead of 7. However, the implementation requires that we implement it using quantum operations like Hadamard, T, and so on. But this doesn't work if you want to simulate it using a Toffoli simulator or using a reversible simulator. So what we're going to do is we override the behavior of this AND gate to act as a controlled NOT gate or a controlled NOT gate operation instead. This is the main implementation for the simulator of the second blog post, a more advanced reversible simulator. The main class for the simulator, as shown here, is still pretty small, but extends a little bit the functionality of the previous version that we have seen. First, it takes a user parameter, throw on releasing qubits not in 0 state, that can control whether we would like to throw an exception whenever we release qubits not in the 0 state. That can be helpful for debugging when we expect that we would like to release qubits only in 0 states. Further, as illustrated by the problem with the AND gate, we can override the behavior of the AND operation by simulating it using a CC0 operation, not getting into the problem that the imply AND and also related operation imply low depth AND are in fact using quantum operations for the implementation of that operation and would therefore not be simulatable by a reversible Toffoli simulator. The processor class itself is also more advanced. One main difference is that the simulation values are not stored in a dictionary anymore, but more efficiently in a bit array, which internally uses 64-bit integers to store 64 bits, and then we can dynamically grow it whenever the capacity exceeded using some growing strategy. We define some helper functions to get a value from the simulation values array or to set a value and insert values. Whenever we allocate qubits, we have this dynamic growing strategy that doubles the size of the array whenever we exceed its capacity. And in releasing the qubits, we can now check if we do have the exception enabled that we want to throw when we release a qubit non-zero state, whether this qubit is in fact in the 0 state, and throw an exception otherwise. X and controlled X are implemented in a similar way as before. And in addition to the previous version, we also can do assertions on a quantum state using measurements in the Z basis. For more details, I refer to the blog post and the samples repository. In this last example, the third simulator that we built, we're going to write Q-sharp execution traces into QPIC circuit diagrams. Notice that these are like the execution traces of a Q-sharp program and not the Q-sharp program itself, because we simulate what we see in the execution of a program. As an example, if we have an if-else statement we will only go into one of these branches, and in whichever branch we go, this will decide what will happen with our trace and what will end up in our cubic diagram. As an example, we use this simple T injection circuit over here. As you can see, it consists of an operation barrier, but there is no barrier operation inside Q# or the standard libraries. We have added this as a custom operation that only does something with this simulator. What it does, it draws this squiggly line into the circuit diagram that we see also here. We generate this diagram by using another custom operation, which is called save picture. The idea is as follows. You call save picture with a file name, and this starts tracking all the quantum operations that we now see in our trace of the program. And it finishes recording these operations when we call the adjoint operation of save picture. And we can make use of Q-sharp's within apply statement to wrap this into a single call for save picture, where we have save picture in within block and all the code that generates traces that we want to capture in the circuit diagram in the apply block. The simulator to translate execution traces of executions of Q-sharp programs into circuit diagrams using QPIC is a bit more involved and spread around multiple files, which I illustrate now. The actual simulator itself is again very simple. It just derives from quantum processor dispatcher and is invoked using a processor class that is defined separately in the processor file over here. This itself is also pretty straightforward, and I only want to give a brief overview of what's inside here. It keeps track of a dictionary of file names to text that we build up for every picture that we want to do. So we can scope different circuit diagram pictures. It doesn't have to be the whole program, it could be like part of the program. And we build up these programs bit by bit whenever we hit an operation that we would add into the diagram using this function add command, but I don't want to need to go into detail here. It's more interesting that you can see that how we use it. For example, we add this part of QPIC syntax that uses a W operation whenever we allocate qubits, or an X whenever we call an X gate, and so on for various different operations that we can execute intrinsically. Y, Z, control Z, Hadamard, S gate, the adjoint of S, T adjoint, and further and further. But remember, there was this function barrier and save picture in the example. These are defined in a separate Q# file that comes as a library together with the simulator. Two operations, save picture and barrier, that have no implementation as a default case. That means if I run it with any simulator, quantum simulator or resource estimation, just nothing happens. It acts like a no operation. But we define a behavior for these operations for our custom simulator to generate QPIC circuit diagrams for the execution traces. Here's an example for the barrier class. As we extend the QPIC simulator, which is our main simulation class, by implementing the barrier operations as C# code from inside. And we have access to our quantum processor instance on which we then can call to create a new command, in this case barrier, for the QPIC file. For save picture, similarly, remember that we use save picture in this way that when we call it in the forward direction, we're going to open a file, and when we call it in the adjoint direction, we're going to close the file. So we implement two different operations, body and adjoint body, and in the body, which is the forward direction, we add a new file name and an empty text to the pictures dictionary that keeps track of all the pictures. And when we are done with operation, we call the adjoint of save picture. Then we're going to write all this text that we have collected into the corresponding file name and remove this picture from the dictionary. This concludes my talk. I hope you got a good idea of how to write your own custom simulators in Q# using the Microsoft Quantum Development Kit. If you have some ideas about your own simulators, or you would like to see more details about the examples I've shown today, I welcome you to have a deeper look into the blog and the corresponding samples that you find in the Microsoft GitHub Quantum repository. I also invite you to check out other resources that teach more about Q#, the Quantum Development Kit, its community, and the execution on partner hardware.